Okay, so before we try to answer this question and talk about specific latent heat, I'm going to revise or recap something which you may have done a while ago. I'm going to draw a graph of what happens when you heat up something through its different states of matter. So let me just plot this first, or draw this out, and then we'll discuss it. Okay, so ignoring these little bumps here and here, it's supposed to be pretty much straight, and then flat, straight, flat, straight, and along the side here, the way that when you did this experiment, if you did this experiment, or even if you talked about it, the x-axis was probably labelled time. And the y-axis would have been labelled temperature. And this is what we call a heating curve. You can imagine the opposite, where you've actually cooled something down. That would obviously be called a cooling curve. So this, I want you to just think about this for a moment. This is a bit odd. You may know the reason why already, but if you didn't, let's just identify what is odd about this. If I heat something up, no surprise, the temperature increases. But at some point, it suddenly stops increasing and just stays the same. And then it continues to increase, and then stops increasing, stays the same, and then continues to increase again. So if we assume that whatever method of heating it is consistent, and we're not, let's say if it's a Bunsen burner, we're not moving the flame away, there's no drafts or anything like that, then we can imagine, rather than that saying time, we can imagine it says energy. So as I give something some energy, at some point it stops increasing the temperature, and then it starts increasing the temperature again, and so on. So hopefully you may, if you do remember this topic, you'll remember that temperature there, where it stops increasing at that point, is the melting point. It stops increasing and flattens out at the melting point. I'm just going to put MP there. And then again at the boiling point. So at the changes of state, it stops increasing. So why is that then? Well, the first thing we need to know is, what is temperature? We think about temperature as just how hot something is. And so if you give something heat, the temperature increases. But we're going to have to change that definition, aren't we? Because that's not what happened here. Actually, what the temperature is how fast the particles are moving around. So the temperature is a measure of the average kinetic energy of the particles. So the kinetic energy is increasing to start off with as I give it energy, and then the kinetic energy stops increasing, and then it starts increasing again. And it actually starts increasing, as you can see, once it's melted, and then it starts increasing again once it's boiled. So it would seem that a certain amount of energy is required to melt it, and a certain amount of energy is required to boil it. We can call this energy here the latent heat. Well, both of them, when you're talking about energy or heat energy required to for it to change state, we use the word latent heat. And more specifically, if we talk about the latent heat to melt it, or the heat released when it freezes, without the temperature changing, ignoring the temperature change, then this would be specifically the latent heat of fusion. And then the other one would be the latent heat of vaporization. So the amount of energy required to melt something is the latent heat of fusion, and the amount of heat required to vaporize something is the latent heat of vaporization. So why is energy required to melt it and to boil it without changing the actual temperature? The reason is that there are what you call is it intra or inter? I can never remember which way around it is, but I'll briefly explain what I mean by these two things. If we have these two particles, let's say two molecules of water near to each other, and maybe they're bonded in a pattern so as to form a solid as in ice, then there's forces between each molecule, and then there's forces within the molecule between the atoms within each molecule. One of them is called intermolecular bonds, and one of them is called intramolecular bonds. Okay, so I've just looked it up, and let's imagine these are two molecules, then molecules of water, whatever it might be. The forces that they feel to each other are called intermolecular forces, and then within each molecule there's atoms that are attracted to each other, and the forces that attract them are intramolecular forces, so in or bonds. So that's within each molecule. We're concerned with the intermolecular bonds or intermolecular forces. So the energy that's being given for it to melt is essentially providing them to overcome these forces. And when they do that, they don't actually move any faster. They just have enough energy to eventually overcome these forces. And the energy that they gain is actually known as potential energy. So as you give this substance, whatever it might be, energy, it will first of all gain in kinetic energy, and then it will gain in the kinetic energy will stay the same, and then it will gain in potential energy around this period, and then gaining kinetic energy again. So you've got potential energy is what is required to overcome the bonds, and then the kinetic energy is just the energy it has to allow it to move it around faster or slower. The total energy, that if you add up the potential energy and the kinetic energy, you would call that total energy internal energy. So it's called internal energy because if you used to see a glass of water just sitting there, seemingly not doing anything, well, there's actually a lot going on, isn't there? The particles inside the water are moving around quite quickly with kinetic energy, and they also have this potential energy, which has allowed them to not stay as ice. So the sum of the potential energy and the kinetic energy is what's known as the internal energy. So I'll stop that video, and that's just basically introducing latent heat and just recapping this heating curve, and also going over the three different types of energies there.